So yeah, I'm Giuliano Iorio from the University of Barcelona. In this talk, I'm going to show you some comparison between the binary black hole merger rates from LIGO, Virgo, Kagra events and the one from models. That is, all the results are mostly based on a paper that we recently published. It was led by Cecilia Sgalletta. These are the references if you want to give a look in more details. So let me start from the question here in the title. Are models over predicting binary black hole mergers? The answer is quite simple. Sorry. Yeah. This is, the answer is yes. It is kind of summarized in this very nice plot by the nice review by Hiriam Ander for Broek-Harden, in which here we are seeing the local binary black hole merger rate as inferred by LIGO, Virgo, Kagra from GWTC3, and here I overplot the result from GWTC4. Now we start to have more than 150 events that we can use to make this inference, and so the constraint on the rates and local rates and the evolution of the rates with redshift start to be quite tight. And in green, here we can see many different predictions from the isolated binary evolution channels that will be the focus of this talk. Starting from 2010, even before the first detection of binary black hole mergers, to very recent one. And you can see that clearly many of the models are on the right. There is a bias toward higher merger rate density, and even with an excess that this can be quite significant. So now, yeah, this is okay. To try to understand what we should fix, what we should improve to like match the inference from LIGO, Virgo, Kagra events, we have to note that there are two main ingredients when we want to make a prediction of our merger of binary black holes. The first one is related to stellar and binary evolution physics, because it's what set the efficiency and the delay time. So the efficiency is the number of binary black hole mergers that we have for a given amount of star formation, and this also depends a lot on metavicity, is an important parameter, and the delay time is essentially the time necessary from the formation of a binary of two massive stars to the formation of black hole and then to its merger. And we have to correlate this with, convolve this with the cosmological evolution of star formation rate density and metavicity as a function of redshift. Altogether, this can be used to make a prediction of the merger rate density as a function of redshift. So the aim of our work was try to understand what happens if we use like state-of-the-art and updated prescription for model both of them. Should we improve the match or not? So for this, we for the first ingredient, the efficiency and delay time, we need to use population synthesis codes. These are codes that are able to evolve millions of binaries up to billions with simplified, with this analytic, semi-analytic prescription from stellar binary evolution. There are many of them available. Most of them are public available. And some time ago, just for fun, I kind of created sort of a map of all these codes in which the cities here are the codes and the river are stellar evolution models. The idea is that if a city is close to a river, this code is based on this kind of stellar evolution models. And you can see that we have a cluster here. These are like what I call BSC island. They are updated version of a main progenitor that was the BSC code by Jarrod Darley. And all these codes are based on stellar evolution models produced by Onno Pols in '98. And many of the predictions I showed you at the beginning were based on that code. For this work, we use another kind of codes that I put here in the interpolators. These are codes in which the stellar evolution is taken into account by interpolating stellar evolution models. Stellar evolution tracks. So they are a bit more flexible and they allow to use modern stellar evolution models. For this work, we use 7. That is one of these code that is publicly available. We develop it and we combine it with the most updated stellar evolution model by the Parsec group, the one produced by Guglielmo Costa. They span a quite wide range of metavicity from population 3 to population 1 and also masses reaching up to 2,000 solar masses. Running millions of binaries, assembling different metadicity, also different assumptions for the common envelope efficiency, we actually obtain the first ingredient, that is like the efficiency as a function of the metadicity. That can be seen here, and a typical property that is common in many of these simulations is that the efficiency is higher for merging binary black holes at lower metadicity. No, this is a bit too. Okay. For the second ingredient, I think one of the main also point of the paper, we compare two different approach to take into account how the star formation density and the metadicity evolve as a function of redshift. We use two other public available tools like Cosmorate and Galaxy Rate. Cosmorate use an average metadicity star formation rate density evolution based on Madao and Fragos. 2017, and here you have a free parameter, an additional free parameter that is the dispersion of the metadicity as a function of redshift. And depending if you use a small value or a large value, you can have a very tight correlation between redshift and metadicity, or something that is more dispersed. But both of them are not really accurate description, also based on recent observation that we have a high redshift. So we use also these more detailed models based on this tool Galaxy Rate. Here, essentially, we pick galaxy from a galactic mass function that is redshift dependent, and then we assume star formation rate and metadicity of, depending on the mass of the galaxies based on recent prescription. And also in this case, we obtain a metadicity redshift and star formation rate density distribution that is much more realistic. So now the idea is to understand if using a detailed models for the second ingredient and modern stellar evolution track for the first ingredient, if we obtain a better match or not. And the answer is not. This really clearly shown here by this plot showing the binary black hole merger rates as a function of the redshift. In gray here, we have what is fair from the GWTC3 for 90% confidence interval. GWTC4 will be a little bit lower, but not that different. And all these other lines are different models that we explore. We explore more a combination of more 360 parameters. And you can see that the model that seems to match better the data is actually this based on, say, average evolution of the metadicity with a very small dispersion. This is actually the less accurate of all the models that we tried. All the other models that sample also uncertainties, for example, on the star formation rate mass relation, that are this family here in particular is what we consider more accurate. They produce an even higher excess of binary black hole merger, especially at the local redshift. This is quite significant. So why this is happening? Actually, is quite simple to understand. Just comparing again, the formation efficiency as a function of metadicity and the relation between metadicity, redshift, and star formation rate density. Now, here I'm not showing just our model, but this is from a paper of Dike and so on, in which there are many models coming from different codes, different papers for the formation efficiency of merging binary black holes, and you see that all of them predict a quite high efficiency at low metadicity. Now, in the accurate models, we have this significant tail of star formation density at low metadicity that is present at all redshift. And this is where the population are really efficient in producing binary black hole mergers, something that we don't see in the, let's say, more simplistic models in which this region here really is not that important. So essentially, more accurate modeling means more low metadicity star formation and more efficient merging binary black hole production, and this produces excess. Now, before going to the conclusion, let just me also show this. We recently published another paper by Federico Marinacci, in which this time the second ingredient, the cosmological revolution, is taken into account considering cosmological simulation. In this case, the Millennium TNG. In this paper, we presented a tool called AREBO-GW that essentially can combine results from population synthesis. In this case, we use the 7+ parsec models with cosmological simulation, and we again can obtain the evolution of merger rate density as a function, of the merger rates of black holes as function of redshift. And again, also in this case, what we obtain from the models is significantly higher than what is obtained with GWTC4 events. Okay, so what does it mean? What we have seen in this talk? Well, first of all, there is clear that models in general tend to over-predict the binary black hole merger rates. I'm talking about the isolated binary evolution channel. And in this paper, we explore many different detailed models for the cosmological evolution of star formation rate density and metadicity. And this seems not, the uncertainties of this model seems not to be the reason why we have this mismatch. So where is the problem? I would say likely in the first ingredient. So binary evolution physics and its implementation in population synthesis code. I have now no time to show you other plots on that, but if you're interested, I can show something later on or discuss. Thank you very much for your attention.
Great. Questions? Okay, yes, and Tasia's handing out mics.
Hi, wonderful talk. I'm Cheyenne Chariot from Caltech. So when you do these population synthesis to make predictions on the LIGO rate, do you ever check other types of binaries to see if those rates are generally order of magnitude similar to observational constraints?
You mean other products like, I don't know, X-ray
yeah, like
binaries?
Let's say you can match the LIGO rate, but you get a factor of 1 million more high mass X-ray binaries in it.
Yeah, no, this is a very interesting point. Not really in this work, but this is, I think, what is really needed to be done. And this is also what is, I think the community is going toward this direction, not using just like Virgo Kaga events, but try to combine them with other observables. It's really important. It's not made in this work, but yeah, this is what we have to do.
Hi, thank you. One of your conclusions was that the excess cannot be explained through the uncertainty of the cosmic star formation rate, but I wondered, what were your assumptions about the first clusters? What were their initial mass functions? There's a lot of extra things that we don't really know or very well constrained, especially in the high redshift. So what did you assume there? Yeah, so actually, I think we try to sample all the uncertainties that we can, actually. So, for example, for the star formation rate, the relation between star formation rate and the mass of the galaxy, we have these three models from the literature, plus we also use some custom slope at low masses for the galaxies where stuff are more uncertain. And we also sample different star formation metadicity mass relation, and we also sample different minimum mass for the galaxy. So we sample what we think is like the largest uncertainties that are present at the moment at the model, and even this uncertainty can be quite important. For example, yeah, you see here we have a model that is quite below to the others. This is because it's based on extrapolated data at high redshift. I think this is not enough. Even taking into account all these uncertainties is difficult to just say this uncertainty is star formation rate density, so the mismatch could be just that.
So I wanted to go back to Cheyenne's question. I agree it's very important to try and make comparisons to other populations. The big problem with any X-ray binary source is that we don't have treatment of selection effects there. So, of course, we can make predictions of X-ray binary rates from the populations, but the observed situation, the observational situation is that we just have numbers in our galaxy, in other nearby galaxies, but they're not corrected for selection effects. And the selection effects of X-ray observatories are extraordinarily difficult. And I have Tom right next to me. I've had long discussions with him and Dipto Chakrabarti, and they cannot be modeled. So another population is pulsars. Very well modeled. We can model the selection effects. But then on the theory side, we have a whole new layer of uncertainties of magnetic field evolution, initial pulsar periods, assumptions, etc. So the models there are much weaker. The gravitational wave sources are the sweet spot of the best of two worlds, but they are only one handle. So.
Well, maybe we can have a quick question from Matthew because he was first. And then the next speaker, Sasha, could you set up?
I wanted to ask about the mass dependence of the discrepancy, because you showed integrated quantities for the rates.
Yeah.
But
this is an interesting point that we did not explore in this work, but of course this is the next step. The first idea was just to look at this just rates. I agree, it's not the complete story. We should look also at the mass distribution at the speed, maybe. Yeah, so it has to be done, but not. It was not done for this work.
Great. And everyone who didn't get to ask a question, please save it for the discussion at the end. Thank you.
Yes.
Okay.